2 or 1 or 0 is your total probability. So if I do this and I put in these values in my calculator, then I am going to say, oh yes, look at that. When my output comes out, I really do indeed get 0.6875. Check. It's exactly the same as my PDF. All right, now moving on to the next question. My next question, part E, says using the binomial stored in your stats editor, add up the P of zeros, P of ones, P of twos. So what I can also show you how to do is how to put this and use your calculator to get these numbers in the data register. Now in the data register, of course, this is going to be a decimal value, so this would be 0.0625 in your data register. This is going to be, of course, 0.25 in your data register. This one in your data register is going to be 0.375, and then this one again 0.25, and then this one again will be 0.065 in your data register. 0.0625 in your data register, but those values would be in your data register. And so you could go to your data register and you could get these three values here, the probability of x being less than or equal to 2, and you could add those up. Now the other thing that we might be looking to do would be to use a table that would be given in a book. So books have binomial probability distribution tables, and those can be used just like what I am describing in your data register as well. So I want to actually grab one of those tables and show you really quickly. So I'm going to have to go ahead and pause because I'm not sure where if I have one of those binomial probability distribution tables or not. So let me finish writing this. 0.0625 is for 0, plus 0.25 for 1, and then plus 0.375 for my 2, and then this again would add up to 0.6875. And let me pause now and get those tables. Okay, so here's a binomial table. And so what we would be looking for in this binomial table would be the n, which is an n of 4, and then we have probability of success of being a 0.5. So what we'd look at is right here in this table, this value from here on down to here, those are the probabilities. Now the deficit of the table is that these tables only show to 3 decimal points. So I don't see the 0.0625. I don't see the 0.0625, right? Because we're truncated all at 3 decimals. So I get all of these, but I'm missing a 10,000th from each of the last two probabilities. But that's how you would use this table. And this is what your calculator is basically mimicking. And here are your random variables, 0, 1, 2, 3, and 4, right? This tells you what your maximum n is, and then again you have to find your p-values. So this is an old-fashioned way basically of having a lot of different binomial probabilities, because calculating binomial probabilities without the use of something like the TI's distributions menu was a little bit complicated. So that's how to use that table. And that is in the back of Triola's book, and it's in the back of most statistics books. All right, so now moving forward, we're going to go ahead and take a look of getting more than 2 defectives in a batch. Well, getting more than 2 defectives in a batch, that is just the following probability, right? Let's use notation here. So the probability of getting more than 2. Well, the probability of getting 2 or less and more than 2, those are complements of one another. So this is the same as 1 minus the probability of x being less than or equal to 2. So instead of reinventing the wheel, doing, oh, that's 3 and 4, you could also do that this is the probability of being 1 minus 0.6875. And so that is going to be 0.3125. Now I do those really quickly in my head by thinking of I need to make a 9, a 9, a 9, and then I need to make a 10. So 3 and 6 make 9, 8 and 1 make 9, 7 and 2 make 9, and 5 and 5 make 10, and that'll make that go all the way up to 1. I know that's kind of a crazy way to think about it maybe, but that's how I do it, and that's how I pop those off pretty quickly. All right, now moving on to the next problem. We can take a look at using this binomial PDF to do the same thing. And so the binomial PDF, obviously you would be adding up these two. So the, let's take a look at G here, and let me just put it right here. G, no, that's not G, oops. Not G, it's part E. So E, that would be the probability that x is greater than 2, and that would be the probability that x is equal to 3, plus the probability that x is equal to 4. Now the purpose of doing this like so specifically and writing all of this out is to give a lot of relationships between what this less than or equal to and greater than or equal or greater than 2 is, and just really to kind of help you with the use of the CDF function a little bit later on. And so this we would get 0.25 and then plus 0.0625, and the 10,000ths place, obviously we have nothings to add to the 5 here and nothing to add in the thousands place, and then the 6 and the 5 will add to 11, and then that 1 will carry and that'll be a 3, and so we have 0.3125, which is the same value we see that we got here. All right, now moving on. We're going to let you have a turn. So you're going to calculate the probability of getting exactly 2 heads in 9 flips of a fair coin, and you want to answer each of the following questions related to this. So what I would recommend you do here is that you go ahead and you turn off the video and you try to come up with your probability distribution function, and then make sure that you can do it with your calculator as well, and just kind of work all of the aspects of this problem, and then turn back on your video and listen to the solution. So if I want to do exactly 2 heads in 9 flips of a coin, that would be the probability that x is equal to 2. When x is the number of flips, or the number of heads, right, in 9 flips. So that's what my x's represent, and I'm flipping the coin 9 times, so my n is going to be 9, and the probability of getting a head when I flip a coin is 0.5, and therefore that's going to lead to the probability of a failure, 1 minus the probability of a success, also being 0.5 here. Now, the first problem says verify that all 4 conditions are met for a binomial probability distribution function. So the first condition is that we have a fixed number of trials. So fixed number of trials, that is met because our 9 flips. So 9 flips of a coin, that's the fixed number of trials. And then condition number 2, I'm going to say is we have a success versus a failure, right? And there's 2 possible outcomes. That's another way of putting that, and that's more commonly the way that it's put these days. And the 2 outcomes that we can come up with here are that you get a head or a tail. So head versus a tail. And our success and failure translate directly this way, right? Our success is ahead. And then there's constant probability of a success. And that constant probability of a success, every time you flip a coin, it's a 50-50 shot to get ahead. And so that probability of success doesn't change anytime you flip, so the probability of success is equal to a 0.5. One flip doesn't affect another, right? Now, the last one that I have to make sure is that the trials are independent. And yes, the independence here, the every time I would take 9 flips of coin, 9 flips of a coin doesn't take things out of the population, and therefore I know every single time I have the exact same opportunity for the same outcomes to happen. So this is not affecting ability to have the same outcomes. So one trial doesn't affect the other. We're not taking things out of the same, out of the population. So not affecting the same possible set of outcomes. Okay, so now that is that second one. All right, now I've done all of these possibilities here. And now I know that this is binomially distributed. So one of the things that you really are going to be focused on later on is these 3 things. These are going to be super, super important for us to be able to recognize a binomially distributed random variable and to do inferential statistics on it. So I would like my students to really, really be able to do that. And I do ask that on tests because I want them to have that ability. Now, the second thing that we note, I already noted these before, so let me go ahead and rewrite these. We have n number of trials, right? N is the 9 flips of a coin. The probability of getting ahead is 0.5. The probability of getting a tail is also 0.5, 1 minus the probability of a success. And our x is the number of heads, right? Just to denote this, and we will have the possibility for these things is going to be 0 through the number 9, right? So that is all of the possibilities. Now, we want to use the defining PDF formula to be able to write this out and find out what the probability is that we're being asked to find. So this probability that x is equal to 2 is what I'm asking for. So when I say that I want you to use the defining formula, that says that you have 9 factorial, that's the n, over 2 factorial times 9 minus 2 factorial, that's the combination formula, probability of a success 0.5, raised to the second power, that's the number of successes we have, probability of a failure, that's 0.5, and that's raised to the 9 minus 2 power. And that's what I'm asking for here, using the defining PDF formula. This is the defining formula. I want you to be able to write out what the probability of x being equal to 2 is going to be.